Hello, and welcome back to another video with ItsDrDan, and today I'm going to be explaining to you what is chirality, especially looking at enantiomers and diastereomers. And we're going to look at a bunch of different examples as well to try to explain what this concept is. Now, what this all has to do with is different carbons, just like the one here, that have four completely unique groups around them. So whenever there are four different groups, what can happen is that when it looks at its reflection, they are completely different, right? You are not able to superimpose them. Now, what does that mean if I can't superimpose them? Well, let's say if I have my right hand and I want to wave it at you. Now, you might see like, oh, wait a minute, that's not your right hand, that's your left hand. Well, it's all about reflections, right? Well, let's try to look at this in terms of a camera to try to understand that. Let's use two of me to help explain this. So if I wave, let's say, if I want to wave my right hand just like so, and you can see, hey, wait a minute, they're both waving opposite hands. Well, this is the whole entire idea as waving at your reflection. So if I use my right hand and I wave it at my other reflection, notice how it's waving its left-hand side, and they're both waving completely different hands. Well, if I take my hands as well, and I try to look at them, and I try to look at both your hands, well, you can't overlap them, meaning that if I put them on top of each other, notice how my thumbs are in opposite positions, right? So you cannot overlap them. So they might be able to be reflections of one another, right? So if I kind of show that my thumbs are both reflecting, I can try to show how they're reflections this way, but I can't overlap them. It's the same idea as looking at my reflection, right? Both sides, we could be waving at one another. We're both waving opposite hands. It's the same idea. Look at yourself in the mirror, try to wave to yourself, and you'll notice it's the opposite side. So what does this have to do with chemistry? Well, if you have, let's say, an enantiomer or mirror images of each other, they're each going to have their own completely unique properties behind each of these molecules, especially if you look at things like in biochemistry, where if you have proteins and enzymes and they have to bond to each other in specific ways to allow a reaction to happen, well, if it's not in the right orientation, it's not going to bond. In fact, in some pharmaceutical chemicals, right, one might be a drug that might cure something in your body. The other one might be a harmful toxin, which is something that's commonly found in the world around us. So let's try to take a look at this concept. We're going to be moving through this and trying to understand this. So let's look at some different examples for me to try to explain chirality to you. Let's take a look. In order for something to be chiral, we have to first try to understand not only just reflections, but this concept of four unique groups. So what I have here is I have a circle drawn and I have four different colors. And in the middle of these colors, we have an intersection. That intersection is your carbon, right? So the carbon meets every single different group. So if I have, let's say, my mirror, which I have drawn in blue, what exactly would that reflection be, right? We have completely different mirrors. It's the same thing as looking at the reflection of myself from earlier in this video. Now, whenever we have two chiral carbons, two different chiral molecules, and we have their mirror images, these are referred to as enantiomers, meaning that they are reflection. Notice how the teals line up, the blues line up, yellows line up, and reds. So inside, outside. The other thing that's pretty cool about it is that, okay, well, if I take this thing, I can try to overlap it as well. And I can see, do those different colors line up? Now, one thing that we can always try to do is, well, can I make it where they line up? And we can attempt to rotate this thing, right? Just like so. And I can try to see like, well, does it line up? And it doesn't. There's no way. We just start making different colors. We can't make it line up, which is something that's really, really difficult when we're looking at these types of molecules. So whenever they are enantiomers, that means that they are reflections of one another. However, they are not superimposable, meaning that you cannot overlap them. So not superimposable, meaning no overlap. Now, depending on the molecules you have drawn, you could have chiral molecules that are identical to one another, that maybe are, let's say, in a different arrangement. So let's say if I cut out this one on the right and I re-copy and paste the one on the left, well, if I have this structure, sometimes the molecule just might be in a slightly different orientation. So if you try overlapping it, it might look like they are two completely different things. You might say they're enantiomers. However, you need to make sure you are rotating and looking at molecules because sometimes they can just be identical molecules. Notice how they're both chiral, but in this case, they are both the same. So we're going to look at examples of that in a little bit. Let's take a look at what achiral means, or not chiral. Achiral molecules. What this means is not chiral, meaning that we're going to ignore certain groups around a carbon. Now, what are we ignoring? Well, we want to ignore things with 3 or less unique groups. So we need to have 4 things. So it has to be tetrahedral and all 4 have to be unique. So we want to ignore things like CH3, right? Because there are 3 hydrogens. CH2, that's 2 hydrogens. Double bonds, double methyls, symmetry, things like that. Now, why is that? Well, both of these, you can see I have 2 teal sections of this molecule, meaning that we have 3 unique groups. Well, can't you say, well, they look completely different. They should be chiral. However, one thing that you can do is if I turn this, notice how they're completely the same. And if I try to overlap them, well, their white and yellow also overlaps as well. So we have not only achiral molecules, but they're the same exact thing. You're able to overlap achiral as well. It doesn't have that optical property. Let's take a look at some different examples and see how we can apply this to molecules. Looking at molecules is a lot easier when you are using models. And that's something that's a very harsh reality for any student that is beginning at organic chemistry or in chemistry in general. One of the things that we try to teach our students is that you need to be able to visualize these molecules and try to see what they really look like. We might write them on a sheet of paper, but all these different molecules, they are 3-dimensional. They are things that rotate and move and change, right? So if we are ever to look at models, we can always see that these things have a 3-dimensional perspective, and we need to be able to understand that. And it's really difficult to do, especially at first, but it's something that comes with practice and the more you look at it. Now, when it comes to a lot of these structures, we have to remember our 3-dimensional VSEPR geometries. So let's say if you don't remember for this video, right? One way that I'm representing these, I have lines here. These are always referring to in the plane, meaning what does that refer to? Well, if you think of your computer screen or your monitor that you're looking at right now and it's flat, well, that means that these 2 bonds that are on the left and on the top, they are in line with your monitor, right? Now the wedge, this means that it's coming towards you. So I like to think it's boldly coming towards you. So usually this is kind of darkened and shown as a big bold line. So that means it's boldly coming out of the screen right at you, right? So now whenever it comes to a dash, the way you can think of this is, oh, I'm dashing away, or it's a fade away, right? You see that it is fading into the background. So like this is like it's going behind you or going like behind your monitor realistically when you are looking at this video. Now, if we take this molecule, and the whole idea here is that we want to be able to build these, right? You need to actually try to understand that if we are to put these things together, we need to build it just like we see it. Now, the big thing is I always tell my students is you want to first start with just your carbon atom by itself, right? So I have a black ball here. Carbon is the black one. Now, if we have hydrogen, right? Hydrogen is going in line with the plane. This is going to be flat like this, pointing up. Now, the other part is that we have a hydrogen, as you can see on the right here, is going to be pointing out. So we're also going to put that flat in line with each other. Now we have a chlorine that's boldly coming out towards you. So we're going to put that chlorine right there, coming right at the camera. And then we will put the bromine all the way in the back. Now, being able to build models is something that's a very crucial skill. So let's say if I want to do the exact same thing, and let's say if I make a mirror image of that, well, what exactly does that mean? Is this something that's chiral or achiral? Now, when we are looking at both these, right, we can try to analyze these different models, and we can try to compare them to each other. Can we make them as mirror images, right? So the whole idea is that, let's say if I have them both facing each other, and we can see that, all right, we have the two red ones facing each other, the white ones are in line with each other. We can see that these are complete mirror images of one another as a result. And when they are mirrors, well, are they enantiomers? Well, that comes down to identifying, do we have four completely different groups? And one thing you can see is that there are two hydrogens here. So what does that exactly mean? Well, we don't have four. So this is an achiral molecule. They can still be mirrors of one another. However, they need to be chiral in order to be enantiomers. So going back to that, well, that just means that we have two chiral, so we have achiral molecules, sorry, and they are mirrors. However, they are achiral. Let's take a look at the next example. Okay, our first example. Are the following molecules enantiomers, or are they the same molecule? Now, in order for them to be enantiomers or the same, what does that exactly mean? Well, same just tells you they're identical, not that they are achiral or chiral, just that they're identical. So in order first, we need to determine, are they chiral? Well, if I go through these, I can try to always highlight that I have four completely unique groups. So we can see we have a chlorine, a bromine, an OH, and an H, right? So we have four different things on each of these molecules. So what that tells you is that we have two sets of chiral molecules. Now, how can you tell if they're mirrors, especially when they're not drawn that way? Well, the easiest way to do it is by using model kits and to build them, put them in your perspective. So that way you can see, do you have the same exact molecule? So that's what I did. So what I usually always try to do is I try to see, can I reflect them? And then what I'll do is I'll see if I can overlap or superimpose them to see, hey, do I have the exact same structure? So here I have both of these different molecules. So I have the one that we had on the left-hand side, right? I have the OH kind of pointing towards you guys. And then I have the chlorine and the hydrogen. They are in the plane, right? So I see the OH out front, and then the chlorine and the hydrogen in the plane. Now, the other thing that we're going to be showing here is that if I look at these, I have my other one as well, and I built this one too. Now, the thing about it is it's not in the same perspective. So what you want to do is you want to line up, let's say if we make both the OHs face each other, we have the hydrogens face each other, and then I also have both of the chlorines in the same spot. And really what you can see is that, hey, both of these, all these different species are on the same side, and it's like you have the little OHs waving at each other, like the reflection that I showed earlier, right? So both of these are mirrors of each other. So notice how everything is a mirror. So we can see that they all line up as well. So these are referring to that they are enantiomers of one another, right? So these are mirrors. So now when it comes to a mirror, one thing that you want to try to do for yourself is attempt to rotate these in your head to see like, okay, how does this entire thing change? And one thing that you usually can see with enantiomers is two of the groups are usually flipped when you have the enantiomer. So you notice the hydrogen and the chlorine, they're flipped of one another on this one chiral center. So most likely this has a chance that's going to be a reflection when it's just one chiral carbon, right? So this is the idea. Now let's try to take a look at a different one. Let's say if I propose the same question with a different molecule. Let's take a look. So now with this type of problem, there are two ways to do this one that makes it a little easier. What we're trying to do is see, are all the groups in the same general position now, or are they enantiomers? So if we want to look, notice how the CH3s are in the same spot. So one thing that this kind of tells you is that when it comes to a CH3, so that's what I'm holding now, the other portion rotates like a pinwheel, right? These bonds, they can rotate. So if it's a single bond, they can rotate. So one thing that we can actually see with this molecule is, let's say if I rotate each of these positions around like it's a pinwheel. And what does that exactly do to the structure? Well, if I do that, well, how's that going to change? Well, I will have a CH on top. I'll have my bromine all of a sudden on the bottom. And then I'll have my chlorine will move to the right-hand side of the molecule, just like so. And the CH3 is the part that we were holding. So what do you see about these two molecules now? They are identical to one another. So these are the same molecule or identical. So when you were going through these, try to see, can you hold one part to be the same and then rotate the other three like it's a pinwheel? Now, how does this look up close? Well, if I take this exact same model and I hold it up to, let's say, another form that is identical to it. So one thing we can kind of see if we hold up those chiral carbons is that the reds will line up, but notice how the blue and white does not quite line up. So what we can attempt to do is line up all the pieces just like so. And you can see the blue parts are generally in the same spot, and the white parts are in the same spot, the red parts are in the same, that they overlap with one another, making these the same molecule. Let's take a look at diastereomers and how we can determine these types of structures. Diastereomers are something that's very, very different and can be a big struggle for introductory organic and biochemistry students. So in order for a diastereomer to be possible, you have to have at least 2 chiral carbons. They cannot be mirrors of each other, and they cannot overlap, meaning they are not superimposable. These are things that are commonly seen in biochemistry, especially revolving around Fischer projections, commonly found in the carbohydrate family in biochemistry. So if I have the following structure here, so I have a biochemical species. Now what we're going to do is we're going to draw the mirror image of this. So what I do is I have these kind of pre-prepared down here. So let's say if I take that mirror image and I bring it up top. Now, one thing we can see is that we have 2 complete reflections of one another. These are referred to as enantiomers, just like we did earlier. Notice how the OHs line up. So this is what the trick is to try to figure out, is there a diastereomer? Remember, they cannot be enantiomers, so how can you tell? Well, what I'm going to do is I'm going to highlight the OH groups. So you can see that those things are highlighted, right? And let's see if I can pick a better color. So OHs are highlighted. Notice how we have 3 OHs on each side. It's a pattern, right? OH, OH, OH. Let's take a look at, if I put another molecule up here, and we'll put another line down. So in order to have, let's say, a diastereomer, let's do the same thing, where now I'm going to highlight the OHs again. So if we can look, notice how the pattern does not match up. Right, on the right-hand side, we have OH, H, OH. So what that tells you is, hey, this is not that 3 OH combo. So compare your sides. Look at a side. Now, what is this a diastereomer in reference to? Well, it's a diastereomer to both of the other structures. So let's say if I label these structure 1, structure 2, structure 3. So the way to do this is that 1 and 2 are enantiomers of one another. Now, what are diastereomers? Well, 1 and 3 are diastereomers, right? And 2 and 3 are diastereomers. So what that means is that all of the structures are diastereomers in reference to number 3, but they have different kind of meanings or connotations behind what kind of diastereomer. And this has to do with carbon numbering. So, for example, if I number this like carbons 1, 2, 3, 4, and 5, so starting at the most oxidized on top, what changes? Well, if I compare number 3 and number 1, notice how carbon 3 changes. So what this is referring to is a C3 epimer for 1 and 3, meaning that carbon 3 flipped. So that tells you that it's an epimer of the other structure. Now, in terms of 2 and 3, well, what flipped? Well, 2 and 4 flipped. So it's kind of like a diepimer. There's doubles. But generally, we only refer to it for 1 carbon when talking about an epimer. So when it comes to a lot of the carbohydrates that are naturally in your body, like glucose and all the other, like lactose and a lot of these other carbohydrates, especially the 6-carbon species, we ingest many of these different sugars, but a lot of them, they're just differing by one OH that's being flipped. Each of these cross sections up here, these are all chiral carbons, right? They all have 4 unique groups, but one of them is switching, right? So all these have 3 chiral carbons that are here, but you see one switching. So that's the idea. The trick is look at each of your sides, and if you see one flipped, you have a diastereomer on your hands. Now, I hope that this video helped in terms of chirality. Keep in mind you're looking for 4 unique groups. Please watch my follow-up video on how to find chiral carbons, so that way it can better help you understand chirality and to better master this. This has been Dr. Dan here, and please hit that like and subscribe button, and come back for future videos on Introductory Organic to help you pass your organic chemistry course. I hope to see you all in the future, and I hope you all have a wonderful day. Bye now.